Thank you. So I'll try to improvise my talk after the presentation of Dr. Pilar Muñoz Calero. I can now focus on some specific aspects.
Vamos a ver dónde estaba. Ya quitamos este. Este era el mío, ¿no? Sí. Y esto está... Ahora no lo veo. Acá sí. Vale. Y el mando era esto, ¿no? Bien, después de esta exposición...
Right, as I said, after that excellent presentation, I will focus on phases 1 and 2 of biotransformation. Is this working? Yeah, I had the pointer pointing the other way. Well, let's see. Before discussing some specific aspects of biotransformation of the xenobiotics, let's start with a description of a new phenomenon. A new phenomenon that started in the 20th century. In the middle of the 20th century, we had become exposed to chemical products. And the chemical products, of course, the chemists are not responsible for that. They are synthetic, and we're exposed to these substances. And we should include also drugs in this group. I'll try to summarize, because this is really a very extensive topic. Over the past 40 years, we have identified these substances that are harmful. In the beginning of the 70s, we started to work on what was called enzymes that metabolize some drugs, drug metabolizing enzymes. I believe that that terminology is not appropriate. I think in the body, we cannot have drug metabolizing enzymes. And the same is true for the toxins. Enzymes, the drug metabolizing enzymes, are new agents, synthetic agents that did not exist in the body. That's why we call them xenobiotics. And in some way or another, they have to be metabolized and eliminated. From the conventional viewpoint, particularly those that prescribe using the scientific protocol, any drug or any toxin, if they're used experimentally after a rapid absorption, you will have this elimination curve. This is time axis below and concentration and levels in blood or tissue. They have pharmacokinetic characteristics. We can localize them in the brain, blood, or other organs. This substance has to be eliminated from the organism. But you will have a change in this time scale into hours, weeks, months. Most of the drugs that are given, not all, most of the drugs given present this exponential curve. It has the so-called biologic half-life, which is how much time is necessary to eliminate half of the drug that has been absorbed. That's an exponential curve, and it follows certain kinetics. just like in alcohol, for instance. It is not, it is limited, it is enzyme-based, whereas others, and there's no saturation. They're not saturated. Well, as I was saying, while drugs are eliminated after hours, an analgesic has a half-life of 2 or 3 hours, or an anti-inflammatory agent, agents such as ibuprofen or paracetamol. And you have to take them 2, 3, or 4 times a day because they are eliminated. Anti-malaria drugs, for instance, that's taken once weekly because it has a long half-life. Now, for the toxic agents, some of them are eliminated quickly, but this does not mean that their toxicity disappears. We'll focus on that later on. But the others have half-lives of weeks or months. They are short for the phosphorated ones, although they are eliminated quickly. But as they disappear, other substances appear. I'm referring to the organophosphates. This half-life of the metabolites may last for a long time, and there may be substances that have been activated in the organism, a substance that had previously been inert. So that's how it works. Although they are eliminated, you have substances that they had previously activated in the organism. So the anti-epileptic drugs, there is a very narrow therapeutic margin, and it depends also on each patient. The genetic polymorphism in humans, since we're still wild species, so to speak, changes the capacity for drug elimination. In certain drugs, it's so critical that the result can be inefficacy or toxicity. Analgesics, anti-inflammatory, there's a wide tolerance. But you may have drugs that have very, very narrow margin, and you have an individualized elimination curve. Today, we can individualize even further using pharmacogenetics. There can be accumulation of drugs leading to half-life of months, weeks, months, or years. For instance, mercury, it may last for months. But then you have a point of balance, equilibrium, where you have administration of a toxic agent that might be equivalent to 5 times the half-life. And that there's a mathematical formula for that. Let's see. If we get I had this in color before. Well explained. Now I have to do it as if I were in a classroom. Well, this is the time axis level. If we administer repeated doses, we get this curve. Now, the next dose has this curve, and as the dose is repeated at regular times, then you reach the steady state. So balance is maintained, and a good therapist achieves the steady state. Steady state and elimination is the same. When we administer treatment, the first dose has to be a double dose to try to achieve the maximum level quickly, and then later to try to get to the plateau, to get to the steady state and maintain that level. Elimination depends also on this. Methylmercury, for instance, it takes practically 1 year following repeated dose administration, or organochromated products can remain for months and months and months. You have the polychromated ones. You have half-lives that can range from 8 to 10 years. So practically, there's no way of eliminating them from the organism. What does elimination depend on? This elimination, in some cases, elimination of drugs or toxic agents, may occur directly. Rarely, a drug or symbiotic cannot be eliminated immediately. Elimination depends, in most of the cases, on the drug metabolism. And metabolism, in most of the cases, usually occur in cytochrome P450, as we heard. Metabolization of most of this is quantitatively the most important, i.e. the liver. They're in all tissues to larger or greater extent, but in the liver, metabolization of these agents occur. What is the main criteria involved there? Most of these substances, I said before, are fat soluble, and they're not eliminated from the body. They have to be transformed into water-soluble substances so that they can be eliminated through the kidneys. So when we speak about half-life of elimination, we are quantifying metabolism of the substance in the body. This is a description, although there is a complex system of metabolization involved.
No. Ahí lo tengo otra vez al revés.
Yes, I'm pointing it the other way again. Once again, yes, mine had a different design. Well, the most of this, there are different pathways. These are not the only ones, but most of these systems, most of these occur in the reticuloendoplasmic system. That's the nucleus. You can see all these membranes here. That's the reticuloendoplasmic system. So this is the endoplasmic reticulum. They're much more beautiful in color. Yeah, but this is real, the one in black and white. This occurs, as I said before, that started in the 60s and 70s. This we started to work on this at the Royal Society. So this is called the microsomic metabolism. These cytoplasmic membranes, when there is homogenization of the cell and they become vesicles, this occurs. The pharmacists call these microsomes, but these membranes, once the cells are homogenized, once they have been isolated by centrifugation, they're very small vesicles, and they contain the enzymatic reticulum. This is the external membrane of the nucleus, and it contains these folds and occupy a large part of the cytoplasm. And they're directly connected through pores with the nucleus. And here also there is a flow, a flux. These round objects, these spheres here, are ribosomes. And you have a synthesis of proteins. And you have a movement of RNA here, RNA which is in vogue. They're very small RNA that also have an enzyme activity. transcription, activity, and metabolism occurs in the smooth part of the reticulum. This one appears to be simple and homogeneous, but they have different functions, well-differentiated functions. You can see the pores, the nuclear pore, the nuclear envelope, and here you have the smooth endoplasmic reticulum. Here's another view where metabolism occurs, chiefly, or most of metabolism occurs. This is phase 1. Here we have a system.
Se llamaba, antes se ha comentado, el citocromo.
We have this, before I mentioned cytochrome P450. Today, cytochrome P450, well, there are dozens of them now, and they have been abbreviated as CYP followed by a number that refer to the family and the specificity. So it was believed that there was a large variety between individuals. A gene synthesizes P450, or you have different cytochromes of a P450, and that was not clarified until the 80s or the 90s. But this is a system.
P450 que tampoco he tenido.
This is a system. Unfortunately, I don't have my slides here. Well, as I was saying, this is like hemoglobin, porphyrin. This is an enzymatic complex bound to cytochrome 450 and other enzymatic systems that are found in this membrane. Here we have dozens of enzymes with a wide variety of enzymes. Two phases have been described, although some believe that there are 3 phases. We have phase 1. This is the modification phase. During this phase, we have agents that polarize and make the agent soluble so that they can be excreted. This is a variety of enzymes that can introduce reactive groups. That is, you have the hydroxyl groups, nitrogen groups, or you can remove an amine, a methyl, to make them excretable. This is the oxidation system. This is a cytochrome P450 dependent mixed function oxidase system. What the system does is incorporate an atom of oxygen into non-activated hydrocarbons. That can result in either the introduction of hydroxyl groups, NO and S dealkylation of substrate. This is incorporated with oxygen-forming water, and this is the product that is produced following reactions. You have the hydroxyl groups and the radical can be removed or part of the molecule is removed. Well, I don't want to focus too much on biochemistry. If we have a chain here bound to benzene or whatever, dealkylate means that it cuts this methyl or ethyl, and this is introduced. This is what occurs in phase 1. Modification. Incorporate radicals or eliminate radicals, oxidate. This means that this does not mean that the product is not inactivated. The activity is eliminated, but on occasion, it increases also the activity. There are drugs that are not active per se, but it goes through this process, such as propranolol. It is not a beta blocker per se, but it is formed in the cytochrome for P450. There are other activation systems that are not included here. And aspirin, for instance, is not detected in blood. They're hydrolased. And there are many cases of inactivation, and we can detect that the drug or toxic agent level is reduced. We believe that they have been eliminated, but however, they produce metabolites in the organism.
La siguiente, la fase 2,
Phase 2, conjugation. Phase 2, based on the agents that produced in the phase 1, these substances produced in phase 1 are conjugated with other substances. And these activated xenobiotic metabolites are conjugated with charged species, such as glutathione. It's comprised of, well, we don't have that here. It's comprised of sulfate, cysteine, phosphate, I think it's there previously, sulfate, glycine, and glucuronic acid. Methylation, acetylation may also occur. The variability in the human species is so great. We have subjects that may not have one of these pathways. In phase 1, we may have subjects that may not have all of the pathways or may have some pathway missing. And this is important pharmacologically and toxicologically. Then you have phase 3, further modification and excretion. Glutathione can be further metabolized. They can continue to be bound with cysteine, and part of it can be converted into water-soluble substance for excretion. But there can also be toxic activation of this agent. It's necessary to take into account that the more critical point has to do with glutathione conjugation to eliminate the active metabolites. The more toxic active metabolites, those that form free radicals or those that have been transformed into very reactive substances that determine reactions in the reaction with nucleic acids, proteins, and alteration of enzymes.
Para recordar esto, la síntesis de todo esto en
This is the summary of phase 1, oxidation, cytochrome P40 monooxygenase system. This requires also flavin-containing monooxygenase system. Monooxygenase is an enzyme that is in the plasmic reticulum. Inhibition of amino oxidase, a problem that occurred in the 60s and 70s. MAO inhibitors were given, and they were used in the field of psychiatry for treatment of psychiatric disorders. MAO is found in the intestinal barrier. That's the first barrier. It hydrolyzes this amine and many of its components, like tyramine, which are present in food. If this is inhibited, this passes on to blood. And patients treated with MAO inhibitors and those that have a presence of tyramine, wine, for instance, like the Cabernet Sauvignon, produce migraine because of these presence in high amounts. You may have people that take Cabernet Sauvignon wine and they have headaches because of large amount of tyramine in that wine. I said there's the first barrier of cytochrome P40, 450 in the endothelial reticulum system. That's the first barrier. There are substances, active metabolite, that are produced in the intestinal mucosa. This is the coupling of cytochrome P450 with NADPH. You have lots of sterase in blood, and there is polymorphism also, and you have subjects that may not have certain esterases. Today, the capacity for hydrolysis has to be established to avoid the complications. Here you have phase 2. The mechanism is by methylation. The involved enzyme is methyltransferase. You have sulfation. You have sulfotransferases, acetylation, and acetyltransferases, glucuronidation. Yeah, I have difficulty pronouncing that. And here in red, which is important in regard to toxicity, you have glutathione conjugation. Glutathione synthesis with glucotransferase. You have the liver reserve of glutathione is limited. It can be depleted. It can be depleted for many reasons. As in the case of paracetamol, that's a prototype. This is the binding system in the endoplasmic reticulum, P450, which is a heme. All the cytochrome P450, B5, etc.
Esperando, como he comentado antes, la aparición de los fármacos o de los tóxicos. Están implicados en...
Here you have the drugs involved in the synthesis of sterols, in the metabolism of fatty acids, etc. And the most important thing is this one up here, and it is here where I'd like to share with you the following, what they represent from the evolution point of view and why there's so much variability. Why is there so many variability? between individuals. The same drug, the same agent may have a very fast metabolization, may be eliminated very quickly, or could be incapable of being eliminated.
Han evolucionado realmente.
These systems have evolved in the human species. We have a great deal of polymorphisms. They're in charge of eliminating all fat-soluble substances. All of the development of the P450 systems, they occur because they are there to eliminate these substances. You have alkaloids, substances, in some cases they're toxic. Being natural means that they are not necessarily not toxic. They have to be water soluble so that they can be excreted, and there are big differences between species. In humans, if we eat an atropine plant, we will become intoxicated. But a rabbit can eat all the amount necessary, and there's no problem. And there are systems there. When we study population, we see important differences. There is a big variability between populations. If we compare north and south of Europe or east compared to the west, you have rapid hydroxylators, which account for 5% in Spain. It may be 20% in Japan. Why does this occur? Perhaps because they're historical adaptations throughout evolution, the period of evolution, to specific habitats.
Ya diré ahora también que en el momento actual.
This is cytochrome P450. Here is one of the many systems that exist. As I said before, you have CYP followed by a number, another letter, another number. We thought that we only had one with different forms, one cytochrome with different forms. Today, 57 genes that encode cytochrome P450 in humans have been identified. And I'm sure that there's a similar number of pseudogenes. These are polymorphic variants. This represents the family, the letter, the subfamily, and this number that follows that represents the pathway. They are more active. So this explains this wide variability, and it is really complex because there's a series of combinations, possible combinations, so that these metabolic pathways, there are dozens in phase 1, not so many in phase 2, and all of them are under genetic control. Many of them are under genetic control. There are those that cannot do sulfate conjugation and those that have active sulfate conjugation. All of these pathways, many of them are redundant. If one fails, then the other one can offset that failure. This is the cycle of cytochrome P450. It is a cycle of oxygen reduction. That's very complex, and I don't have the slides that details this. Now, if this is the cytochrome P450, and bound to cytochrome P5, and you have oxygen from the air exposure, you have oxidation of iron, you have an electron that will give it pH, and you will have an oxygen. R represents the drug or the toxic substance, and the other one will form the water. And the cycle starts once again. It's oxygenation, reduction, and electron transfer. Electrons are incorporated. Oxygen become 2 atoms. One binds to the drug or the substance, the other one to water. You have catalase and you have hydrogen peroxide formed in this way. Here you have different types of cytochromes that metabolize drugs. The proportion of drugs metabolized by different types of cytochromes. Some cytochromes follow a more a pathway. These are the families in humans. I said before 57 genes and more than 52 pseudogenes. And really, this is rather complicated. But I simply want to point out that although quantitatively most of this type of reactions take place in the liver, some of the cytochromes are also present in other tissues. Practically all of them are found in the liver. In the brain, we have other series such as CYP2, and brain and other areas. I'm sure the same thing occurs, such as the skin, lung. You have clear cells of the lung. They have specific cytochrome that implies toxification, important toxification. Detoxification, for instance, in the case of paraquat. We have, in the hippocampus, we have cytochromes that are responsible for having activation or inactivation of toxic substances. When hydroxyl groups are incorporated, they become transformed. This implies what we call sometimes suicide reactions. Dr. Pilar Calero showed an interesting slide. At that time, there was much controversy. Carbon tetrachloride, carbon fluorotetrachloride. We've had lots of discussions with the chemists because they worked a great deal with carbon fluorotetrachloride. It is used professionally. It has been found that subjects had fulminating liver cirrhosis. In phase 1 of P450, there's a capacity to eliminate chloride. You have a free radical. It's represented by this dot here. And they have this capacity to bind to proteins or fat. And there is complete cell claudication leading to necrosis or fat regeneration. That's why we call this a suicidal reaction. The enzymatic system, the P450 system, has evolved to eliminate substances that are fat soluble and they hydrolyzed. There is no natural organochlorinated substance. So the same phase 1 reaction of oxidation transforms this into a free radical and can only be conjugated with glutathione up to a certain degree. When large amounts are produced, there are reactions with proteins and alteration of all of the enzymatic systems. And this is a type of oxidative stress. This is what we call suicide because of toxic reaction. When we speak about metabolism in phase 1 and even in phase 2, we know that there is a large amount of metabolites that are produced following these different reactions. You have hydroxylation, dealkylation. Some of these metabolites are active. Narcoleptin, if I remember correctly, can act on cholinergic receptors. That is, they may function such like nicotine. This variety of products, we have to know what each of these products do. We have to know what all of these products do. We have to be familiar with each one of these products. Before the 80s, we prepared a profile of an organochlorinated product. We have the metabolites during degradation. They may produce up to 100. And for instance, the production of chlorobenzene, that's a classical toxic substance. They produce some substances that are also very reactive. If you have a substance, hydroxylate, well, it doesn't really matter. There's nothing special about this molecule. During hydroxylation in phase 1, this can become, there can be a formation of double link, and it can be transformed into an epoxy. There is a system of hydrolases, and they're transformed into quinones. This occurs in drugs and many toxic agents. In pesticides also, such as in the case of organochlorinated products, you have chloride, and you can have formation of free radical or an epoxide. This is one of the most common phenomenons. You have activation, toxic activation. Many classical organochlorinated products produce also liver cancer. They're carcinogenic through the oxidation pathway. This occurs also with aromatic hydrocarbons. There are aromatic hydrocarbons, aromatic hydrocarbons that are found in that we breathe, and they're transformed into hydroxylase and products that are highly reactive, and you have a production of free radical if it is not conjugated with glutathione, for instance. We have a protein. A protein will bind with this one. Now with DNA, you have binding with the base and nucleic acid, but in fact, mutation has been produced. You have covalent reaction, a reaction that cannot be eliminated unless there's a breakdown of DNA, for instance. You can have a protein. You can see how many adducts have been incorporated. In astrocytes, we find a series of proteins that have been hyperoxidated by adducts of this type. Now, if the substance that has been formed in small amounts react with certain areas in certain areas, we can have, for instance, acetylcholinesterase. We'll have serine, and this is what happens with gases that are used in wars. They react with acetylcholinesterase. And you have this chain where certain degree of activity can be modified, but they cannot be eliminated. We may have a serious problem if they are irreversible. There are clear cases of that, such as acetylcholinesterase. They were developed as gases used for war, and they may lead to certain manifestations that we are unaware of. So when we speak about phase 1, we're not only referring to oxidation and reduction, but whether we have formation of electrophils or nucleophiles. These reactive agents require participation of glutathione conjugation. You have glucuronoconjugation. This is the prototype for paracetamol. Through the normal pathways, you have glucuronidation. And as I said before, in phase 1 of the reaction, we may have these quinones. This is reactive reagents, and with glutathione conjugation, they can be compensated. We know that the reserve of glutathione reserve is depleted, maybe due to a polymorphism with low reserve of glutathione, or because they have been depleted. Those that have been using pesticides have alterations like malate, ethyl malate. Ethyl malate reacts with glutathione and depletes glutathione reserve with several grams. Of exposure, there can be a fulminant liver necrosis. Now, if you expose, if you want to get rid of someone, you can expose them to paracetamol plus glutathione. Paracetamol is a classical model. Paracetamol is widely used, particularly in the United States. In the 70s and 80s, it was an antithermal agent, and its use was limited. And because of the accidents that occurred after 3 or 4 grams of intake, we had these accidents, and it affected the glutathione reserve. And today, you have even 1 gram of paracetamol in packs of 6 tablets, and you can kill someone with that or produce severe liver injury. I really don't know why they allow 1 gram paracetamol to be sold that easily. You see, you have them in packs of 6 tablets of 1 gram each. So there are many substances, many factors. And we do not know for what reason the glutathione reserve has been depleted. There's a large amount of glutathione. The brain has to be protected against oxidative stress, and there's 6 glutathione transferase, a large variety, each one with greater or lesser activity, and glutathione in the brain is even much more important than the glutathione reserve in the liver. Importance of glutation. You have S-cysteine. Cysteine alone is the only case where we can have the substitution of glutathione. Cysteine can do something, It's not the same as glutathione, but it can do something. And let's see. There are other examples, and you have active metabolites in these substances. This is an organophosphate, malathion. I think this has been prohibited in some countries. Why? Because of a phenomenon that I described. It is desulfurated. It produces this oxygen, which is highly reactive. Malaxon, after exposure, for a short period of time, after a month or a month and a half, you begin to see disorders, peripheral disorders, neurofilamentous anexopathy, and tremor is produced, or intoxications that are produced with parthion. Sulfur is replaced here by oxygen, and this type of reaction is produced. The afternoon, which is so common, leads to very important changes. The organophosphate of this type, it's not the only metabolite. The toxic activation will occur in some cases over a period of time, and they are irreversible. You have derangement of neurofilaments of the nervous system. I already spoke about the epoxides. This is just a review. These are substances that form these epoxides, thereby producing problems in the formation of adducts. Here you have those drugs that can form these different compounds. Anilines were mentioned before, p-aminophenols. All of these products, through the cytochromes, produce reactivity. But the effect will depend also on the genetic characteristics of the individual. So today there are drugs that can be adapted, adjusted to each individual. There are smokers who have a high risk of developing lung cancer, but there are those that can live up to 95 years of age without any problem or risk of having cancer. A smoker may be a slow hydroxylator, slow oxidation in phase 1. You can see the amount of hydroxylation through a test, and that's determined in urine. And glutathione's role for protection has already been mentioned. You can have a hydroxylator that's very active. And cigarette smoke will produce a hydroxylator, and you may have a slow glutathione conjugator. And you may have high reactive metabolites, high levels, and in these individuals you have a higher risk of cancer. All of these profiles, all of these metabolite profiles can be identified in the subjects before this and different products of metabolization have been analyzed. Now today there are tests that show what type of CYPs the subject may have. They may be more active or less active, and this allows us. There are few cases where this is done because it continues to be complex and difficult to perform, but it helps us determine what type of chemotherapy can be used and what type of responses patients will have, the probability of the subject to produce active metabolites, DNA, etc., and their degree of activity. Here we can see how many of these agents and substances we're exposed to can produce modification. P40, cytochrome P40 can be inhibited. There are drugs that induce activity of the cytochrome P450 activity. You can have a de novo synthesis and we'll have more cytochrome P450. And this will lead to a faster metabolization of the drugs. On the other hand, you have the inhibitors of this system. There are a few: urea, taurophils, series of inhibiting drugs, food also, such as Brussels,
y otros tipos de alimentos. Con lo cual, el estatus del sistema
such as Brussels sprouts can produce this effect. But there is also another system which is much more complex. For this, the so-called signaling pathway, this is the ligand, the toxic agent, the symbiotic that enters the cytoplasm and binds to this receptor in the cytoplasm of the AHR. It is complex. It has a lot of several accompanying proteins, enzymes. Once in the nucleus, it detaches from these accompanying enzymes and links to this receptor, forming an heterodimer, AHR with the symbiotic plus this other protein which is a transporter. It is now in the nucleus, and when heterodimer is formed, we have these small sequences of DNA. It may have 5, 6, 7 nucleotides, and they are promoters that activate or may inhibit genes with distant pairs. And you have modification of the cytochrome expression. The 1A1 is simple to determine, and that is used as a pattern to determine the induction of the system. This means that the subject may be in a situation, a different situation vis-a-vis metabolization agents, particularly dioxins. This will determine a permanence in the organism for a long period. So this is a different status of metabolization of the individual. Since we are all different, of course you didn't see that in rats, in laboratory animals, but in humans, since we're all different, there are different reactions, a wide variety of reactions. Why some individuals develop a series of reactions, for instance, in MCS, and others do not, following exposure. In other subjects, this does appear, but that's due to all of these complex factors and mechanisms, the phenotype that modify system expression, genetic polymorphism of the individual. This varies also. And there are variations also based on the geographic location. Thank you.